Okay, so let's look at another example. Sketch the regions bounded by the graphs of the equations and find its area. So you will be given x plus y equals 3 and y equals x squared equals 3. Now I went ahead and did this just ahead of time to save us some time and to try to have a decent graph, but you will have to provide this on your own. Okay, let's do this with respect to our Rx region. So a couple of things we're going to do. We're going to Rx, we're going to draw a rectangle in there, label it dx, and I'll say area is going to be from A to B of our f of x minus g of x dx. So we remind ourselves of some of these things. Let's also make sure we solve these for y equals. So we'll take a few minutes and do that and label each one of these before. Okay, so we solved this one for y. That's our red. Y equals negative x plus 3. Sketch the graph of that. Solve this for y equals negative x squared plus 3. Sketch that. Now, it's hard to tell on this one, although we could probably see using the graph, but let's just pretend that we couldn't tell precisely these points of our x-axis. One of the ways you can find where they intersect is to just set the values equal to each other. So we would have negative x plus 3 is equal to negative x squared plus 2. Get all x terms on one side and solve this. I'm going to pause it and then you can just check your work, because this is some basic algebra that you should remember. Okay, so I just moved everything to be positive values, factored right here, and then found x equals 0 and x equals 1. So x is 0 here, x is 1. We can kind of tell that in our graph because I did a decent job, but if you're not able to, you can always use this method to find your where it intersects if the graph doesn't reveal that to you. So right here we're just going to have 0 and 1. We can either see that from here, or we can see that on the algebraic side of things. So I'm going to say intersect. Okay, I get some scratch work. All right, now let's do our f of x function. So because this is a dx, we want the upper minus the lower. Now let's focus in on our rectangle. The upper rectangle touches which function? The blue. Good, so we want the blue function, and the lower part of our rectangle touches the red, so we want to do blue minus red. Now go find that. Blue is negative x squared plus 3 minus, and our red is going to be negative x plus 3. And then we have that as, and the width of our rectangle is dx. Okay, so let's simplify this algebraically. We simplify the inside of that, and we should come up with negative x squared plus x dx. Now, in our previous two problems, at this point we just stopped. This would describe the region, this highlighted region in yellow, but we're going to actually evaluate that and find the area of our highlighted region. So we want to evaluate this. What's the antiderivative of this term? So I'm going to make a note and I'm going to say evaluate. Let's see if I can get a little more room here. Evaluate, and that will give me x to the third divided by 3, and then that negative's out front. I can just put a 1 there. Plus x squared divided by 2, or that's 1/2. Okay, and we want to evaluate that from 1 to 0. Okay, let's check your work. So first of all, antiderivative is negative 1/3 x to the third plus 1/2 x squared. Evaluate it from 0 to 1. So we plug in the upper boundary, plug in a 1. The 0 is easy. I hope you're okay with that. If you plugged in 0 for x and 0 for x, we're just going to get 0. So that saves us a little bit of time. And then you just calculate that, and we find out that this is 1/6 units squared. Okay, this is another example. Remember, you're only given these two functions. This you provide on your own. So whether you use an XY table or you use a graphing calculator to sketch those, find the regions between them. Um, Algebraically, you can try to solve for these intersection points. I'll probably go ahead and put that. I want you to take this one as far as you can. Okay, the first thing I did is I just did some algebra to find the intersections. That's where it's going to intersect for the x values. And actually in your calculations, it doesn't matter if you use the square root of 8 or if you use the simplified version of it, because we'll get a decimal answer. So that's just kind of up to you which one you use. Okay, a couple things I sketched in my d of x, dx rectangle. Make sure these are solved for y equals, which is nice because it's already, we'll have all of our terms in the variable x here. Okay, now we look at our representative rectangle to make sure we do the upper portion touches the blue graph, so it's going to be the upper boundary minus the lower boundary, so that's the red. I'm trying to color code this to make it a little more noticeable. So then that's going to be represent our rectangle. So your next thing I want you to do is to simplify this inside, and then at that point you're ready to evaluate. So go ahead and take this as far as you can. Okay, so I simplified here and I get negative x squared plus 8, then dx. I want to evaluate that. Now what you guys probably did, because I didn't instruct you differently, is you evaluated this from negative 2 square root of 2 to 2 square root of 2. But you also have the option of using an even function theorem because it fits that format. So if you look back at, I think it's Theorem 5.34 in your textbook, and then also in the previous lesson that we covered, you will see that this fits that form. Not only that, let's look at it in a graphical sense. If I was to fold my paper right here on this dotted line, don't you agree with me that these two sides would be the same? Yeah, so we can visually see that. So you can either calculate the area from here to here like this is showing, or we can do from 0 to 2 square root of 2, take this answer and multiply it by 2. So I'm going to do the even function just so you have 2. I'm sure you probably worked it the other way. And I'm going to use the even function to work this out. So I'll pause it now and even function theorem to solve. Okay, so we evaluate 0 to 2 square root of 2. So remember, I'm just going to do this half and multiply that times 2. So if you'll just pause it, you can check through that. Now the advantage to this is my evaluations are going to be a lot easier because I have a 0 involved, so it's kind of probably cuts down about half of the work. But either one should work and be consistent, so hopefully you got that. Okay, this next example I kind of pre-worked, and I'm just going to talk our way through this. So first of all, if I was given y equals x plus 6, I graphed it, sketched, made that sketch there. Y equals x cubed function, that's the purple line. Okay, I sketched it. Y equals negative 1/2 x is the red. I sketched it. Okay, so we did all that. We know we're supposed to do that first. If we're going to do a dx, let me label that. If I'm going to do a dx, then I need to solve them all for y equals, so they can all be in terms of x, right? So y equals, y equals, y equals, that's taken care of. The next thing is that if I look, I purposely highlighted two different regions because if I put a rectangle in this side, you can see that the upper boundary is blue and the lower boundary is red. But what if I look over here to the right? The upper boundary is blue, but the lower boundary is purple. So in this case, it's like I had to do split it into two shapes or two regions and do the area of region 1 and the area of region 2. and then add those together to get the entire area of the region. And that makes sense because we do that in geometry often. So I just kind of labeled these regions. This was our rectangle, so it was the blue function minus the red function, blue function minus the purple function. And so this first one is from -4 to 0. So this is going to be our highlight. X is -4 to x is 0. So that's going to be that. And then it's going to be the blue function, x plus 6, minus the red function, because the red's the one that's touching the bottom right here. So this is the area of region 1. We would simplify right there. Then we would evaluate it. And our algebra comes out to be that this is 12 units square. So this guy is 12 units square. Okay, so then we move to the blue region, and I just called this area 2. And so the interval, their limits, lower and upper, are going to be 0 and the x value of 2. We can tell by those points. So that's why we have 0 and 2. Upper limit is the blue. Lower limit is the purple. So I want to do blue, x plus 6, minus the purple, which is x cubed, dx. We're ready to evaluate now. So take the antiderivative and evaluate it using your fundamental theorem of calculus. We solve that and we find the blue region, or our region 2, is going to be 10. Now to get the entire, we take the area of region 1, add it to the area of region 2, and we finish with 22 units squared.